Water expands 1,600 times as steam. If wet recycled asphalt flash boils inside a hot mixing silo, the pressure can rupture steel containment. On the other extreme, if the burner flame directly hits the binder, you get blue smoke. That is toxic pollution, and it means you are burning your yield. To recycle a road, this facility must navigate a narrow thermal corridor. Heat the material enough to melt, but keep it cool enough to prevent combustion. Here is the engineering behind reclaimed asphalt pavement, RAP, the one-stone journey. Asphalt is a viscoelastic material. Over time, UV radiation oxidizes the oil, making it brittle. Traffic loads crack the surface, but the chemistry is reversible. This facility turns a waste pile into a strategic material stockpile. Today, we will track the journey of a single stone. We will see it milled from a highway, fractionated by size, superheated behind a flame shield, re-oiled by chemical diffusion, and tested in a lab oven. It starts at the failure point, the road surface, milling and comminution. We do not bulldoze the road, we machine it. A cold milling machine, equipped with a drum of tungsten carbide teeth, grinds the pavement. Sonic sensors control the cutting depth to within millimeters. The goal is to remove the oxidized wearing course without damaging the structural base layers underneath. The result is RAP, reclaimed asphalt pavement. However, this raw rubble is a chaotic mixture. It contains dust, crust, and large agglomerations of pavement. If we fed this directly into a new mix, the road would fail immediately. A durable road relies on a specific aggregate skeleton. We need a precise gradation curve. Large stones for load-bearing strength, medium stones for locking, and fines to create the mastic. Constraint, aggregate uniformity. If the gradation fluctuates, the road develops air voids. Water penetrates these voids, freezes, expands, and potholing begins within one season. Therefore, the RAP enters a sizing circuit. Unlike mining, we do not want to fracture the stone itself. We only want to break the bond holding the stones together. We use horizontal shaft impactors tuned to a low rotor velocity. This shatters the asphalt clumps, but preserves the geometry of the original aggregate. The material is then fractionated into distinct piles. Fine RAP, bituminous sand, and coarse RAP, bituminous stone. This separation gives the plant operator total control over the mix design. The thermodynamic conflict, the dryer. Now we face the hardest engineering challenge, heating. To mix asphalt, the binder must be liquid, requiring temperatures typically between 150 degrees Celsius and 170 degrees Celsius. But RAP introduces two volatile variables, moisture and hydrocarbons. RAP piles are stored outdoors. They soak up rain. To heat wet rock, you first have to pay the energy penalty of the latent heat of vaporization. You must boil off the water before the rock temperature can rise. Moisture load, industry limit often approximately 5%. If moisture content spikes above critical levels, the burner must work exponentially harder. If the dryer cannot vent the steam fast enough, it overwhelms the filtration system, forcing a plant shutdown. The binder coating the rocks is a petroleum product. The blue smoke limit, a standard burner flame, can exceed 1,000 degrees Celsius. If this flame touches the wrap, the bitumen oxidizes instantly. You lose the valuable glue, and you violate emission permits. To solve this, modern plants utilize counterflow drums. In this design, the heat transfer is compartmentalized. The superheat zone, virgin aggregate, new sand and stone, enters near the burner. It is exposed to the direct flame and superheated, often reaching temperatures exceeding 250 degrees Celsius. The shielded zone. The wrap enters the drum roughly halfway down, protected by a steel collar. It never sees the fire. Conductive transfer. As the drum rotates, the superheated virgin rocks mix with the cold, wet wrap. The heat transfers via conduction, rock-to-rock contact. This creates a steam flash that dries the RAP and melts the old binder gently, keeping it below the oxidation threshold. So far, we have stabilized the aggregate size and neutralized the moisture. Now, we must repair the chemistry. The baghouse, filtration. While the drum spins, a massive fan pulls air through the system. This exhaust stream is filled with fine dust and steam. It cannot be vented to the atmosphere. It passes into the baghouse. Inside, thousands of hanging fabric bags filter the air. But this dust is not waste. It is mineral filler, essential for the mix. The system pulses compressed air to shake the dust off the bags. It falls into a hopper and is augured back into the drum. Dust to binder ratio. The airflow must be balanced. If the return ratio drifts high, the mix becomes dry and brittle, leading to cracking. If it drifts low, the mastic becomes unstable and soupy. The plant automation constantly adjusts the draft to maintain this balance. Binder rheology, the chemistry. The stone is hot, the moisture is gone, but the old glue is still dead. The bitumen on these rocks has been baking in the sun for 20 years. Asphalt binder is composed of 4 fractions: saturates, aromatics, resins, and asphaltenes. Engineers use a blending chart to calculate the recipe. They determine the viscosity of the old binder, the viscosity of the new virgin binder, and the dosage of the rejuvenator. Too stiff. Underdosing results in thermal cracking in winter. Too soft. Overdosing leads to plastic deformation under heavy truckloads, known as rutting. The binder is chemically active again. Next, we manipulate the physics of coating to save energy. Mixing physics. Warm mix. We have superheated virgin rock, heated ROP, and chemical additives. They converge in the mixing zone, twin shaft pug mill or drum finish. The goal is coating. We must encapsulate every millimeter of surface area. Traditionally, we used high heat to lower the viscosity of the oil so it would flow. Today, we use water foaming injection. Right before injection, a nozzle introduces a microscopic amount of water into the hot bitumen. The water flashes to steam, expanding the binder volume and creating a foam. This is not adding volume to the road. It is increasing workability. The foam acts as a lubricant, drastically reducing the viscosity without adding heat. This allows the plant to coat the rocks at temperatures typically 30 degrees Celsius to 40 degrees Celsius lower than standard hot mix. Less fuel burned, less thermal aging of the wrap binder, and a safer environment for the paving crew. Quality assurance, the proof beat. The mix travels up the drag slat conveyor into the silo, but before it leaves the yard, we need proof. A lab technician pulls a sample for the ignition oven test. The sample is weighed and placed in a furnace heated to over 500 degrees Celsius. The asphalt binder burns off completely. The reservoir. The truck leaves the scale. What was a pile of rubble 3 hours ago is now a monolithic waterproof pavement capable of supporting 80,000-pound loads. Because asphalt involves no permanent chemical hydration, unlike concrete, which cures irreversibly, this cycle is theoretically infinite. The limiting factor is not the material. It is the precision of the thermodynamics and the accuracy of the rejuvenation chemistry. The road network is not a disposable asset. It is a material reservoir, stockpiled energy waiting to be tapped. For more breakdowns on civil engineering materials and industrial recycling logic, check the archive.